Alright, in this video we're going to continue kind of down the list on that summary of convergence and divergence for series sheet, and we're going to look at the comparison, the limit comparison, and the integral test. And I'll just kind of look at these one at a time and then give a couple of examples. So first, the comparison test. Alright, for the comparison test, this is very similar to what we did when we looked at integrals, and we would compare one integral to another to see whether that integral diverged or converged, and this is very similar. So kind of notice the different pieces here. You have an inequality, so things I would expect to see in the work is an inequality, and then I would expect to see also why either the sum of b sub n converges or why the sum of a sub n diverges. And we're picking a different series to compare our original series to, and so kind of a big hint on this one and is to use stuff that we know that's easy. So using geometric series or p-series, use one of those to compare it to. So I kind of look at the original and see how close it is to either a geometric or a p-series, and then I try that. And then the third thing I'd expect to see is a conclusion. So the conclusion would be this part, then whatever you had to begin with either converges or diverges. All right, let's do some examples. So let's look at the sum from n equals 1 to infinity of cosine squared of n over n squared plus 1. Now, this is one where if you take a look at kind of the full series and what I see in there, I notice the n squared. I notice the n squared that kind of looks like a p-series. The cosine oscillates, and so that's why this is kind of a good candidate for the comparison test, especially because cosine oscillates between -1 and 1. So cosine oscillates between 1 and -1. So cosine squared would be in between 0 and 1. And if I divide this by n squared plus 1 and divide this by n squared plus 1, 1 over n squared plus 1 is going to be less than or equal to 1 over n squared. Because if I have something bigger in the denominator, the whole thing is smaller. Right, so there's my inequality. There's kind of the first part of this. So I'm looking at 1 over n squared, and so that's what I'm going to compare it to. So I'm going to look at the sum from n equals 1 to infinity. This just starts at the same place the original one does. 1 over n squared. And so here's my second part. I need to state why this either converges or diverges. And let's see, it's a p-series with p equal to 2. And 2 is bigger than 1. I highly suggest that you're kind of looking at your summary of convergence and divergence sheet as we do this and looking under the p-series part of this. So p-series, p is equal to 2. It's bigger than 1. So that means it converges. And lastly, the conclusion. Since the sequence is bigger and the series converges, so the bigger series converges, the smaller one would have to converge. And so my conclusion is that the original one, which was smaller, cosine squared of n over n squared plus 1, converges. And we used this was the comparison test. So converges by comparison test. All right, and that's it for that example. Now notice that I didn't box anything on this because really there's nothing too box. There's no kind of answer at the end. I mean, maybe converges, but the whole process is really important in this, and the whole writing out of everything is really important. And so if I were to box everything, I would just box everything. So let's do one more example here. Let's look at the sum from n equals 1 to infinity of 8 to the n plus n squared over 7 to the n. Now, when I look at this one, and again, I'm searching for something that's easy to compare it to. So I could either use, I've got some sort of a p series going on in here, or I've got this geometric series. And we used p series in the last one, so let's use geometric, although it might be possible to compare this to the p series. But let's compare it to the 8n over 7n. So if I add something to the top, that makes it bigger. So 8n plus n squared over 7n is going to be bigger than 8n over 7n. These are both bigger than 0. That's important. And there's my first thing. There's the inequality. So now secondly, I want to show what happens to 8 to the n over 7 to the n. Now, this is a geometric series. So again, I suggest that you look at that summary of convergence and divergence sheet. Under geometric series, r is what's raised to the n power. So r is 8/7, and 8/7 is not less than 1. It's bigger than 1. And so this series diverges. All right, now I have to look back to the inequality and make sure that this works in the correct direction. Because if the series diverged, but it was bigger than the other one, I'd have to stop and use something else. It wouldn't work. So I'll say that again. If this series, if that sequence was bigger, so if these were switched, then we couldn't use that one. We'd either have to pick a different series to compare it to, or we would just have to pick a different test. But because this one is smaller and it diverges, so the smaller one diverges, it will force the bigger one to also go to infinity and then diverge. So here's the conclusion. The original, the sum from n equals 1 to infinity of 8 to the n plus n squared all over 7n diverges, and we used the comparison test. Okay, so there's a couple examples of comparison test. And next, let's look at limit comparison. So some of the important things to show on this, we will have this limit. So one of the things you'll have to show is the limit of a sub n over b sub n. Now, again, you're going to pick something. You're going to pick either an a sub n or a b sub n, and the other one will be your original. So you need to find that limit. You also need to show why either the sum of a sub n or the sum of b sub n, whichever one you picked, show why that converges or diverges. Now, what's nice about that, so that's this part. What's nice about this is that if this limit is bigger than 0, then they both converge or they both diverge. So there's none of this kind of wondering whether the inequality is the right direction or not. If your limit works out, then it's great. There is this other kind of part, it doesn't show up a lot, but if the limit is 0 and one of them converges, then the other one does. So you can use that, although that doesn't happen very often. And the only other thing that I want to mention on this that's really important and easy to miss is that L is a finite number. So that means that if you take the limit of a sub n over b sub n and it's equal to infinity, you can't use this test. You would have to go to a different test. And this is different. Divergence test, the first one we looked at, if you get infinity, it works. It's fine. But this one, if you get infinity, you cannot use this test. And the third thing we need to, of course, state is our conclusion. All right, some examples. Let's look at the sum from n equals 1 to infinity of n squared divided by n cubed plus 1. Now, this one leads me to limit comparison because of the polynomials. I have n's raised to numbers, and I always use limit comparison with these. It works out really nicely. Now, on the bottom, we have an n cubed. And on the top, we have an n squared. And so just notice that if I multiply by an n on the top, I would have the same powers, and then the limit, you just choose the numbers out in front of those terms, the terms with like powers. So my key is to use something where I can make the powers the same. And so I'm going to use 1 over n. You'll see in just a minute why I'm going to use 1 over n and not n. And this is because when we take a limit, as n approaches infinity, of one of the sequences divided by the other, the order here does not matter because either they both converge or they both diverge. So order doesn't matter, just 1 over the other. That limit is the same limit of n squared over n cubed plus 1 times n over 1. And now I have an n cubed in the numerator, an n cubed in the denominator, a 1 out in front of the n cubed in the numerator, a 1 out in front of the n cubed in the denominator, and so this limit is 1. That limit is 1, and I go back and look at the test, and if the limit is greater than 0, then they either both converge or both diverge. So now there's the first part, there's our limit. The second part, we need to show why what we chose either converges or diverges. This is a p-series with p equal to 1, and 1 is not bigger than 1, and so it diverges. And so the conclusion would be that the original would also diverge. N cubed plus 1 diverges, and we just used limit comparison. All right. So the trick on this one is really to pick most likely a p-series on these, where your powers will end up being the same. Let's do another example. Let's look at the sum from n equals 2 to infinity of 2n squared divided by the square root of n to the 7th minus 2n squared plus 1. All right, I want to make those powers the same. In the top, I have an n squared. In the bottom, my biggest power is a 7/2. So let's see, if I subtract these, 2 minus 7/2, 2 minus 7/2 is, let's see if we get a 2 there and a 4. 4 minus 7 is 3/2. Okay, so now I'm going to try this. I'm going to try this with the power of 3/2. So n squared, n to the 3/2, and n to the 7/2. Do I have the same powers there? So 3/2 plus 2. 2 is the same thing as 4/2, which is 7/2. Okay, I've got the same powers. I'm going to use 1 over n to the 3/2. Okay, let's set up a limit. The limit, as n goes to infinity, of our original 2n squared divided by the square root of n to the 7th minus 2n squared plus 1, all divided by 1 over n to the 3/2. This is the limit as n approaches infinity. Now, we checked to see that n squared plus n to the times n to the 3/2 was n to the 7/2. So when I flip and multiply here, I'd get 2n to the 7/2 divided by the square root of n to the 7th minus 2n squared plus 1. And now I have like powers. My biggest power on the top is n to the 7/2, and there's a 2 in front of that, and my biggest power in the denominator is 7/2, and out in front of that is a 1. So my limit is 2. 2 is greater than 0. There's the first step. Second step, I need to show whether 1 over n to the 3/2 converges or diverges. This is a p-series. P is equal to 3/2. And that is bigger than 1. So it converges. And since that one converges, the original will converge. So thirdly, I'll state my conclusion. The sum from n equals 2 to infinity of 2n squared divided by the square root of n to the 7th minus 2n squared plus 1 converges. And we used limit comparison. Okay, let's look at the next test. So there's a couple examples for limit comparison, and I want to look at the integral test next. Okay, the integral test. I've blown this one up pretty big because there's definitely some details in here. So the first thing that you need to show is actually three-parted. You consider whatever you have for a sub n, you look at that as if it were a function. And you need to check / show that it's continuous, that it's positive, and that it's decreasing. If any of those things fall apart, then you cannot use this test. So that's the first thing that you need to do. And a lot of times these are sort of visual checks, but you at least need to write it down that this does happen, that you've actually had that thought. Then the next part of this is to find an integral. So again, you're treating that sequence that's in the series, you're treating that sequence as a function, and you integrate it using the same bounds. So you've got the same bounds as the sum. And this does go to infinity, so you're going to have a limit in that integral. So you evaluate that integral and see if it converges or diverges. If the integral converges, the series converges. If the integral diverges, the series diverges. And so that's how that one kind of works out pretty nicely as well. Converges and converges, or it's going to diverge and diverge. All right, let's do some examples. So let's look at the sum from n equals 2 to infinity of 1 over n times natural log of n. All right, so those first things. So first thing is that it needs to be continuous. So if we look at 1 over n, natural log of n, well, n can't equal 0, because we'd have a division by 0. And let's see, natural log of 1 is 0, so n can't equal 1 either. But these are okay, and it's okay because n starts at 2. If it didn't, then there are some other tricks, like you can plug in n equals, well, we couldn't even plug in n equals 1 and 0, so I guess it just wouldn't work in this case. All right, the second thing. So this is showing that it's continuous. It is over the interval of the series. Positive. 1 over n, natural log of n. It is going to be positive as long as n is greater than or equal to 2. That's all that really matters, is just whatever those bounds of the sum is. And thirdly, it needs to be decreasing. So is 1 over n plus 1 natural log of n plus 1, that's the next term, is that next term smaller than the original? If you have something bigger in the denominator, the whole thing is smaller, and so yes. Right, so it is continuous, positive, and decreasing. And now we need to find the integral. And so the fourth thing, we need to integrate from 2 to infinity, same bounds as the sum, 1 over x natural log of x. I switched the variable to x's. We're used to integrating with x's. All right, so on this one, let's see, if I choose u as natural log of x, du would be 1 over x. So I'd end up with the integral of 1 over u, which is natural log of u. And I'd have to take a limit as different variable, b approaches infinity, of the natural log of the absolute value of u, and u is the natural log. And I have to evaluate that from 2 to b. Sorry, those are separated. So if I plug in b, natural log of b, as b gets really big, natural log of something big is big, and then natural log of something big is then really, really big. So this is going to go to infinity. So this diverges, the integral diverges, and so the sum from n equals 2 to infinity of 1 over n, natural log of n, will also diverge. All right, so we looked at 3 different tests today. We looked at the comparison test, the limit comparison, and the integral test. And on the next video, I'll continue kind of down that sheet, going over each one of the different tests.